Welcome back to Chem 237, Chapter 2 Notes. Today we're going to be talking about hydrocarbons. So, what are hydrocarbons? Hydrocarbons are compounds that have only carbon and hydrogen, C's and H's. Example would be ethane, which is C2H6. So what is important for hydrocarbon? There are four important C's of hydrocarbons, of chemical structure of hydrocarbons. And we will be covering those in this chapter. So your first one is composition, which is basically the chemical molecular formula. The next one is constitution, which is how are they bonded. Next one is configuration. That is how are they arranged in 3D. And is the fourth one is conformation, which is spatial relationship between bonds of adjacent atoms. So hydrocarbons can be divided into two major branches, which is aliphatic, which can be further broken down into alkenes, alkenes, and alkynes, while you have aromatic hydrocarbons, which are your phenyl rings and your benzene rings. Some examples you can see are ethane, ethylene, and acetylene. So some important facts about alkanes are they're saturated, so no double bonds, while alkenes and alkynes are unsaturated. These are all aromatics are also unsaturated, and they're also called aromatics because they have a smell. Um, so if you're ever trying to identify a molecule later in your chemistry journey, if they have a smell, there's a high chance they have a benzene ring or something like that. The basic chemical formulas, so unbranched formula for each of these aliphatic hydrocarbons is CnH2n plus 2, CnH2n, and I'm sorry, I should probably put more space. C, Cn. So this is for alkanes. I should probably do it better. Alkanes. This is for CnH2, and this is for alkenes. And CnH2n minus 2 is alkynes. And what I mean by chemical formulas, like if you're doing unbranched chains, it is basically, for example, if you're doing ethane, uh, and you know that you have two carbons in ethane, then you know the chemical formula for ethane, it's going to be C2 and then H2 times 2n plus 2, which gives you C2H6. And this works for any of the other unbranched alkanes. So if you do an octane, octane has 8 carbons, so C8H2, 8 plus 2, so That's 16, so C8, 16 plus 2 is 18, so H18. That would be the chemical formula. And I mean, if you want to confirm it, you can do that. So CH3, CH2, CH2, 3, 4, 5, 6, 7, and then 8. So if we count these up, you got 3, 5, 7, 9, 11, 13, 15, 18. Yep, so it's CaH18. So these formulas is what I was referring to. Speaking of branching and unbranching, so if you'd have an unbranched hydrocarbon chains, you can probably switch back to white. You can write them as N normal or like or N alkene, something like that. Uh, which um think about it as a straight spaghetti noodle, straight noodle. So something, some ways of writing unbranched would be C, like I showed earlier. Should be CH3, CH2, CH2, CH3. This is butane. Right? Another simplified way would be getting rid of the bonds. So CH3, CH2, CH2, CH3. This is another way of writing butane. And then even further simplified, you can just write it like this, CH. I think these are all acceptable ways of writing unbranched um, alkenes. So here's a table with a bunch of values. So you got methane, your simple one, which is just CH4, CH4, right? As you can also see in this chart, as you keep adding more hydrocarbon units, which are just CH units, your boiling point and melting point increases. Also, if they're unbranched, your density also, if they're unbranched, then your density also increases. It has to do with stacking, which we'll cover later. But yeah, I mean, you can look at this graph, but as you increase CHs, you increase BP slash MP slash density. Okay, these rules apply when you have unbranched. This is unbranched, by the way. It's very important to remember that these are unbranched. Um, yeah, another type of writing these branches or unbranched chains is just drawing them out as structures. So um, another like drawings of unbranched chains is something like this, where you're just drawing lines, and these lines indicate bonds between two carbon. So some assumptions we are going to talk about are that these vortices, we assume these are carbons with four bonds on them. So usually these carbons will be, in this case, since it's the edge carbon, it'll be bonded to three hydrogens and bonded to another carbon. Um, this carbon, the second one right here, this is one, this is two. The second carbon would have two hydrogens and two carbon bonds, something similar to that. So this is another way of drawing. This is called the line structure. This is another way of drawing un unbranched chains. So moving on, I would probably be drawing a lot of unbranched chains, but some examples um, for alkanes, such as butane, would be like this. One, two, three. So one, two, three, four. That's butane. Alkenes, butene. I'm gonna draw this as 2-butene. So that means there's a double bond on the second one. So that's butene and then alkyne. This would be 2 butane, one, triple bond, something similar to that. So these are line structures. Um, Another variety of unbranched chains is also cyclic alkenes or cyclic compounds, I guess that's another way of writing them. Cyclic alkenes. And by their names, we can probably guess they have a ring structure, so something like this. This would be cyclo, because there's 1, 2, 3, 4, 5, 6. This is cyclohexane. I feel like just showing the table doesn't really help, because that would mean you'd have to pause a lot. So I'm gonna write them out. Just the important ones, aliphatic. I feel like I'm gonna write down the compound names just so it's easier instead of um just showing you the table. So for some carbon compounds, we're gonna start with methane. Methane is just your single carbon. It doesn't really. So methane. This is just methane. Right? There's also meth. Usually people write it as meth. Then you have your ethane. I'm gonna start drawing it in line structures. It's easy. This is your ethane. This is eth. People usually write it as eth. It's also ethane, right? Then you got your propane. One, two, three, butane. So let's try that again. So this is propane, pro, propane. Then you got your butane. That's butane. Or after butane, you don't really write short forms for them. So this is one, two, three. Sorry, one, two, three, four, five. That's pentane. I would like you to see the pattern. So basically, you have you can break it down. So your major chain is, let's start with hexane. So one, two, three, four, five, six, right? This is your main chain. If you have six, then you have hex, which stands for six. And then at the end, the suffix, you're writing ane because this is an alkane. Since this is an alkane, you're writing it as hexane. But I hope you see the pattern. If I change it to a double bond, the ending or the suffix would change to hexene. If I had a triple bond, it would change from hexene to hexine. Hexine, like that. So I drew it to hexane, which is up here. If you want to do the rest, you should probably look at this table, learn it. This part is a lot of memorization, unfortunately, but if you learn this, you will remember it in the long run and be very helpful for you guys. Um, Simplifies a lot of your job. So, I mean, cyclohexane is a good example, but we can go higher or lower. So, cyclopentane looks something like this. This is cyclopentane. This is your cyclobutane. And then this is your cyclopropane. Some interesting things about An interesting fact about these three in specific is all of these carbons here, all of these carbons here are sp4 hybridized, which is an important detail to know because they have four bonds, right? So two to a carbon and two to hydrogen. So it's an sp4 hybridized, and we know sp3 hybridized, and sp3 hybridized has an angle of 109.5 degrees. So all of these, as you can see, are especially cyclopropane is less than this 109.5, right? So these are highly unstable because all the bonds and connections are being forced all together, which really doesn't sit well with the structure itself. So it's highly unstable. And instead of being a perfect triangle like this, it actually bends. It becomes something like that, where it still has three sides, but it's all bendy. So it looks something like this. Uh, that's just a sidetrack. Next thing that we're going to cover are some other important Lewis structures that we need to know, which are also on a table format, which are these ones. So these are isomers. Isomers basically mean different compounds. Well, I cannot spell today. Isomers are just different compounds with same chemical formula. In this table, they're given as substituents, which we'll cover later, but it is important sometimes to know because in this, this is propyl group. Sorry, let me redraw that again. It's actually the right amount of carbon there. This is your propyl group. Don't worry, we'll cover this later in a second. This is your propyl group, and this is also, sorry, this is also a propyl group. But to distinguish between these two, we give this one the iso name. So you can distinguish between them. Isoprop Y. Iso. It basically tells you the shape of the substituent. So for you have other ones that you need to know, which are given in this table, such as isobutyl, um, sec-butyl. These are structures. So this is a secondary butyl group. The secondary carbon, which we'll also have to cover. I'm getting ahead of myself. This is a secondary carbon group. So it gives you the structure. So sec-butyl, and then this is third butyl. All of these are, so this is a tertiary carbon. So you need to know that. Majority of these are just gonna boil down to memorization, which unfortunately is something we have to do for organic chemistry. But if you can learn these, practice drawing out structures and naming them, it gets easier and easier. But by the way, if you add substituents to a unbranched chain, so for example, if you go from butane, such as this one, to a methyl butane, so this is just butane, and you go to this is one, two, three, you go to two methyl butane. Don't worry, we'll cover the naming conventions in a minute. If you go from this to this, the boiling point, melting point, all of that, it's impacted and it becomes lowered. So this guy would have a greater boiling point slash melting point compared to this one because it's unbranched compared to it being branched. So they're less densely packed together, and that impacts the different structures of your compound. So for example, butane would have a melting point of like 0.5 degrees Celsius, and isobutane, which something like this, one, two, three, four. Isobutane. This is non-methyl. This is isobutane has a melting point, or sorry, the boiling point of negative 11.5 degrees. So you can see how drastically different they are, as an example. Now, how do these names come to be? There's some IUPAC nomenclature that we all need to learn. IUPAC nomenclature. IUPAC stands for the International Union of Pure and Applied Chemistry. These folks came up with all the naming systems, so it's uniform and common throughout every nation. So this way you would have similar names in the United States and Russia. This was established during the Cold War when element discovery was at its peak and elements were being discovered in a lot of different countries, mainly in Soviet Union and America. And they would name them differently to, bolster their pride and their accomplishments. So you had different names for, like, different Russian names for some elements, and you had different American names for certain elements, and that clashing made it really difficult for scientists to generalize and learn from these discoveries. So they came up with this IUPAC name. So IUPAC has 10 rules, and we're going to break them down step by step and learn. So they have 10 rules. First rule is to find the largest carbon chain. All right, I'm going to really quickly do an example. I'm going to make it weirdly complicated. Cooperates, of course. Something like this. Imagine you have a weird branched hydrocarbon, something like this. So you start counting, right? Count with green. So you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you got a chain that is 14 long, then you can treat this one, 1, 2, 3, 4, 5, and do it use a different color. Let's try red. So you got 1, 2, 3, 4, 5, 6, 7, 8. So that's not the biggest one. Then let's move to blue, I guess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's not the biggest one either. Moving on to a different color. Probably see. You can see the pattern, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So after doing all this counting, we can see that this biggest chain is this one. Let me pick a different color. So the biggest chain we have is this guy over here. It's the green chain. You know what? In retrospect, I should have done it in green. But here. So this is your biggest carbon chain. That is rule number one. So you identify the biggest carbon chain in your given chemical. Then you number the chain, which we end up doing because we have to like find which one is the longest. The next one is the number the chain, right? Like we did over here. So we counted the numbers out, right? Once you number the chain, that gives you the name of the it gives you the name of the compound. So once you're done numbering the chain, it gives you the base name. So this one is 14. So we go back up here, right? Oh, we don't really have 14 here, so I don't know. I might change it. All right, so you number the chain. I don't have 14 here, so I'll quickly look it up. Miss Oh wait, so that would be just your 14 carbons, right? 14 carbons. That apparently is Mistral. If you have a 14 carbon chain, it's Mistral. My wrist, my wrist chain, then I guess. That would be your 14 carbon chain. So if you don't have any double bonds or anything on here, then you can number and it gives you your base chain like formula. I'm gonna redo this one just to make it a little bit easier, right? Count, I'm gonna number the carbon. Uh, Numbering the carbon. Let's redraw this with a simpler version. All right, so let me see an example. All right, let's start with an octane. 1, 2, 3, 4, 5, 6, 7, 8. Right? Let's give it an ethyl substituent, a methyl substituent, right? And propyl. Let's give it an isopropyl substituent. All right, so if we count this like we did before, we'd have start with this one. 1, 2, 3, 4, 5, 6, 7, 8. When you're counting, um, you want to make sure that you assign your substituents the lowest possible value. So if, for example, in this case, they're pretty much symmetric, so it won't matter. But if you number the chain, oh, whoops, number the carbon chain. So in that case, they were all symmetric. But if you have something like this, where you have a substituent here, right? There's two ways to number this. You can either do 1, 2, 3, 4, 5, or you can do 1, 2, 3, 4, 5. You'd probably go with the first way, where you're methyl. So the right way would be this way, where you're going 1, 2, 3, 4, 5. So going this way would be the right one, because you want the substituents to have the lowest number. So in the other case, the substituent would have the value of 4, but in this case, it has the value of 2. So that's how you want to do that. Once you're done numbering the carbon chain, it will give you your basal like name. So for this example, we have 5. So this is pentane, right? So that's pentane. It gives you your basal chain, right? And now number 3, now you move on to number 3, which is identifying. Wow, I cannot spell today. Start with identifying the substituents. So in this case, where we drew the pentane, right? 1, 2, 3, 4, 5 here. This substituent is a methyl, so we identified it as methyl. All right, I should probably go back up and write those out as well. So, for example, when you have something like this is a methyl, this is ethyl. These are all substituents, by the way. I'm just gonna make the big chain bigger. Keep adding them. This is propyl. One, two, three, four. This is butyl, right? You keep identifying them as long as your side chains are smaller. Okay, I have to add another one here to make it small. As you can see, so here's the reason why I added another carbon here, because these substituents are only considered substituents as long as they're smaller than your main carbon chain. So before adding the other carbon, my main chain, which was this, my main chain, which was I guess this one, would have been the same size as the butyl. So I couldn't really, I mean, I would have to separate one of them as a substituent, but it could be either of them. So to make it very clear, since we're just starting, I added another carbon to ensure that there was only one possible spot for substituent, which was down here. So basically, yeah, so you identify all the substituents, then you name the substituents. Step 4 is to name the substituents, which we did with step 3, name the substituents. Once you do this, you have to start adding these names with your number. You have to assign them with the number. So you have the one. Again, you want to make the most complicated one, or like it's alphabetized. So when you start numbering your main chain, you want to make sure that the substituent, which has the earliest alphabet, is at the lowest numbers. It usually ends up being more complicated than that, but for basic purposes, that's what's important. So I'm going to start naming it from right to left. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11, which is, if I scroll back up, undecane. I know all of them till 10, 11 and 12. I mean, I know 12 as well, but 11 is just a little bit foggy in my head. So I had to look up, but yeah, so you have your undecane, undecane, right? And you numbered them. You named them in the previous step. Now, step 5, I'm getting ahead of myself again, is assign them location. And step 5 is assigning location. And assigning location is basically like you pick the most complicated one. Uh, Usually it starts with halogens. I'm gonna pick halogens first. So if you have, so basically halogens are what like fluorine, bromine, chlorine, iodine. Am I missing anyone? Yeah, probably, but uh, you can look those up. So fluoro, this would be your prefix. Fluoro, bromo, chloro, ClH, ido. I hope you're getting the basic idea of, so the first priority is usually halogens, then it is in your alkyl substituents. So your alkyl substituents. You usually pick ones that are most complicated or first in the alphabetical order. So in this case, I chose butyl, right? So it would probably be butyl, ethyl. You probably won't get it done too complicated. It would be butyl, ethyl, then methyl, right? In terms of complexity and in terms of alphabetical order, they line up pretty well. Uh, Propyl goes first. If you see a propyl, you probably want to name it first, even though it is comes later. So it would probably fit somewhere here. It's mostly alphabetical in terms of the order, but other times you can. So propyl would be here, and then you have methyl. That's how they usually organize it. So that's how you would like assign those substituent values. So first would be your halogens, then your substituents. Right. So once you're done with that, um, if you have the next step, step 6 is to group any identical substituents and then give them another prefix for a prefix. So group identical substituents. I cannot spell. I don't think that's, I don't, wait. Big identical substituents. Wow. Kind of brain fog there. Substituent. That's crazy. Okay. You pick identical substituents and then you group them together. So in another example, if you have something like this and you have two methyls here, that's your entire group, right? So you want to start earlier. 1, 2, 3, 4, 5, 6, 7, 7, 8. All right, so you want to group them together. You have two methyls. That means you have a dimethyl, right? If you have three methyls, it would be trimethyl. 4, yeah, you usually don't get more than 4, but if we had 4 methyls, it'd be tetramethyl, right? 5 methyls would be pentamethyl, something like that. So basically, yeah, I mean, I hope you can see the pattern, how that works out, but usually you'd only see 2 to 3 methyls grouped together in this class. So then step 7 is putting it all together. So I'm going to draw and alphabetizing the substitutes. Put all together and alphabetize the order. Right, so if you paid attention to the numbering, then you paid attention to the names, then you group them all together. Some important things you have to know for this step is once you're writing it out, let's do a couple of examples with all of the steps combined, right? So example 1, we just have your simple, let's take simple pentane, right? So you start numbering them, 1, 2, 3, 4, 5, right? So you would just write this as N-pentane or just pentane, whichever one suits your one, right? Next one, a slightly more complicated one would be pentane, but you got a methyl group attached. So you now which side would you start counting from? Left to right or right to left? Giving you some time to process it. I hope you did. You would start from left to right because you want the methyl substituent to have the lowest number. So 1, 2, 3, 4, 5, right? So this would become 2-methyl pentane. So here, if you can see, what we did was first we numbered our main chain, right? We figured out which one was our biggest chain. In this one, it was fairly obvious that the main chain was the biggest one because that's how I wrote it out. Um, and then you numbered the carbons in your chain. So that's what you did. Step 3, you identified your substituent. It was the methyl one. 4 was assign them a location, which was 2, which is done right here. This is your assigning them a location. Step 6 was to group identical substituents, but you only had one, so you didn't have to group any of them. Moving on to a later example, right? 7. So if you have 1, 2, 3, let's make it bigger, right? And I'm gonna add a couple more. So yeah, 2 methyls, right? And then you got 1 purple over here. How would you start counting them? Right to left or left to right? Since we want the substituents to have the lowest value, we're gonna start from right to left this time. So 1, 2, 3, 4, 5, 6, 7, 8. So you gotta So our biggest chain is 8 carbons long, so we know it's a octane. We have substituents on carbon 6, 7, and 3. So how do we write it? So we write 3-ethyl, 6, 7, dimethyl octane. As you can see, these names can get awfully big. So this would be another example, right? So first, as you number your carbons, you figure out which one is the biggest carbon chain. And in this case, it's fairly obvious because I drew it out like that, where I drew my 8 carbon chain first, then I added the substituents. But in another example, where you're just given just random big chains, you have to count and figure out which carbon chain is the biggest. Step 2, what's the number of carbons? We did that. That gave us the base name, which was octane, right? Step 3 was identifying substituents. We did that. That number 3 was ethyl. 6 and 7 were methyl, right? 5 was assign them locations. We did that too. I just said it. 6 was group identical substituents together, which was methyl at 6 and 7. So we grouped them together. You can see that step right here, right? And then 7 was putting them all together. As you can see, you ignore here you can see I ignored the di. So if it was in alphabetical order, right, dimethyl should have been in front. But we ignore any prefixes that are related to quantity or position. So anything like di, tri, sec, or per, anything like this, it gets ignored, right? While anything related, some things don't get ignored. Those ones are related to like isomerism or like different structures. So iso doesn't get removed, neo doesn't get removed, and cyclo doesn't get removed. So these 3 don't get removed because they are not related to quantity or position, just the chemical configuration of how those are organized. So that was step 7. Step 8 is functional groups. This one is a doozy, but I will cover it regardless. Functional groups are different from substituents because functional groups can have like other elements, not just your simple hydrogens and carbons. So 8 is also adding functional groups, and that this can be very complicated when you're doing because they are both in prefixes and suffixes, and I felt it was important for me to cover it in a way that makes sense. So if you start with, okay, I'm gonna draw. Uh, yeah, let me write out the priority first, and then I will write the prefixes, suffixes, and then draw the shape so it's easier for you guys to identify. So the functional groups, these are in priority, by the way. So if you see them, then like if you see them in this order, then like that's how you pick. Geez. So I'll make it'll make sense. It's a little bit complicated, so I'll start. First one is carboxylic acid. This is a little advanced, but it's important to know carboxylic acid. The next one is anhydride ester. I'm sure most of you don't know what these are. Amide. But for the time being, just in Chem 237, you usually don't cover this a lot, but it shows up later. And having a strong foundation really helps out in later Chem series. So I'm gonna just cover it now. Alcohol. Also very important for them, cat. Alkane. Alkene. Sorry, this is alkene, alkyne, and alkane. Right, these are your functional groups. I should have found a table for this. The prefixes is carboxylic, carboxy, then you have alkeno, alkeno, ioloxy, carbonyl, uh, um, alkoxy, carbonyl for ester. Then for the amide, you have amido or yeah, just amido. Then you have your oxo for ketone. Sorry, for your aldehyde. Then for your ketone, it's keto. Alcohol is hydroxy. Don't worry, this will make sense when you do them later. Then this is alky, alkenyl, alkenyl, kenyl. And this is alky. And these are prefixes for suffixes. You have or oic or acid, anhydride, it's just anhydride. There's O8. Geez, what's this like disgusting? Making it smaller. Anhydride. This is not really a suffix, this is the ending term. So I don't have to draw that one there. But anhydride, and this is your suffix, your O8. Then amide. Own. This is A, by the way. All in and all right, so that's how you do it. I'm gonna do a couple of examples because it's very important. So if you have something like this, right? If you have a chain, right, and then you have your double bonded oxygen. So this is a carboxylic acid. So in this case, with functional groups, what you have to do is you have to make sure that your main chain incorporates the functional group. So in this case, if you number these carbons, you'll see 1, 2, 3, 4, 5, 5, 6, right? Okay, I should probably draw them so that let's say make it easier, right? So if you have something like this where you have 5 carbons on both ends, your main chain will always prioritize carboxylic acid first, then anhydride, then ester, then amide, then aldehyde, ketones, alcohol. Um, in retrospect, I think you might not know what these functional groups are itself. their shapes. So I might draw those out as well, make it easier. I'll go over this example later, but let me draw their shapes so you can shape, so you can identify them as well. So you have R. Oh, I haven't covered this notation either. So, but yeah, this is a little advanced, but I guess it's important. R just means an alkyl group. This is just an alkyl group, which you can see from your from the previous pre if it for pre if you look at the prefix, right? Alkyl means just like hydrocarbons. So this is just a random hydrocarbon chain, a random alkyl group. So no double bonds. It's a single bond, branched or unbranched carbon chain. So just imagine some other for right now, just think of R as a butane. This is R, for example, right now. R can be any single bonded branch or unbranched chain, but for example, we'll just take that. That's your carboxylic acid, your anhydrides are this. It's gonna be all over the place with the structure, but this is your ester, your amide. I know they're not in like exact order, but I hope this makes sense. NR3, or sorry, 2, NR2. This is your amide, aldehyde, ketone, alcohol, um, alkene, alkyne, and then your alkane. So that's basically how they look. So now we can go back to the example. So 1, 2, 3, 4, 5, double bond OH, right? So this was our example, right? When we counted, it was 1, 2, 3, 4, 5, or 5 right here, right? So in priority, carboxylic acid takes priority, so our main chain will always be this one, even if those two carbons have the same number, or like if those two chains have the same number of carbons, carboxylic acid would take priority. So instead of being a carboxyl, so I'm not even gonna bother with the name, but I'm just gonna, yeah. So your main chain is gonna be the one with carboxylic acid in it. So it would be 1, 2, 3, 4, 5, right? So that would be, oh wait, so you have to number them differently again. Instead of, now you have to go from right to left. So 1, 2, 3, 4, 5. So most of the stuff basically stays the same. This would be 2-methyl pentoic acid. So those are 2-methyl pentoic acid, right? So this would be the name for this compound. Another example of this would be ethanol. All the partygoers will know this one. So ethanol, this is your classic alcohol that we drink at parties. So ethanol would be written as ethanol, like this. This is 1, 2, and then you have your ethanol over there. Anyway, that's another example. Something, let's do an aldehyde, right? 1, 2, 3, 4. You got your aldehyde. You got an ethyl here. You got a methyl here, right? So procedure stays mostly the same, but again, even if this chain is bigger, we always stick with the chain that contains your, I don't think this chain is bigger, but if, all right, let's do another example where you have, where your main chain is much bigger than the other one. So it's just a substituent. So if you have something like this, right? 1, 2, 3, 4, 5, 6, 7, right? And then you have like, that won't work. You would have to have like two of them. So if you have like an aldehyde here, but you also had an ethanol, you had a, you've had one here, right? That's the only way this would work. So now you would have a substituent, a functional group as a substituent. So this would be 1, sorry, starts here 1, nope, starts with a 1, 2, 3, 4, 5, 6, 7, right? Now you have a substituent on your number 2. So, and that's an aldehyde, and the prefix for aldehyde is oxo, so it would be 2-oxo 1, 2, 3, 4, 5, 6, 7 hepanoic acid. That's how two functional groups work, if you ever get those. So you can see that's the basic stuff remains the same, except functional groups have their own weird way of organizing the step one, and how the naming is all weird. So for step one, when you count the carbons and come up with your parent chain, you have to prioritize certain functional groups if they are the biggest ones present in the chain. So yeah, so for example, in the previous one, right, if you had this 1, 2, 3, 4, 5, 6, 7, then you had your ethanol. Some might say you wait, oh, sorry, just draw it so it looks more like a substituent, right? So you have this. Let's say you draw it out like this, right? Now, the way I've drawn it, it looks like 1, 2, 3, 4, 5, 6, 7, 8. This is your main chain, but actually it isn't. This is your main chain. So 1, 2, 3, 4, 5, 6, 7, 8. This is how you would have to, this would be your main chain instead of the methyl being, because it is just an alkane, and alkene is the lowest in priority, right? So it would be your lowest chain. So this would be, instead of writing it as uh, 2 carbonyl, 2 carbonyl octane, which is wrong. This would be 2 methyl uh, octonic acid. That's how you would write it. So the priority of your step one changes when you're dealing with functional groups. And yeah, basically that's all there is. R and stuff we'll cover later. But in 237, I don't think you'll encounter a lot of this. So it's not a big deal. You don't have to worry much about it, but it's good to know. The next step is, sorry, this was step 8 and 9, I guess, functional groups and double triple bonds. Double bonds. Right, okay, I should probably cover unsaturated as well. Let's do double and triple bond as well. This is step 8 and 9. So although I grouped them together, step 9 involves unsaturated bonds, which are your double and triple bonds. I just grouped them together for step 8 and 9. But basically what you're doing here is you're naming them as well. So if you have, let's say, something like this, right? Where your double bond is here. So nothing changes much. You identify 1, 2, 3, 4, 5, 6. You identify the main chain, and in this one, you want to ensure that your double bonds are in the main chain. Then you identify the location, the lowest number of where the double bond starts. So in this case, it's 3. Right? We're just still following these steps. You count the carbon, you number them carbons, then you identify the substituents, which in this case is a double bond. Then you assign them a location, which we did right here, number 3. And then since there's only one, we don't have to worry much about it. And then like naming them would be pretty much 3-hexene. So this 3 tells you where the double bond is. This double bond is here. So another way of writing it could also be hex 3-ene. When you have a lot of substituents, it is best to write it this way instead of writing it this way. So another example I'm going to show you will clarify how this works. So this way you can also write multiple like bonds if you have them. So yeah, let's start with this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so you got your methyl, you got your ethyl, you got a double bond here, right? You got your triple bond here, and you have, yeah, that's pretty much it. So how would you number these carbons? You would have to start here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10, right? So you have an methyl at 2, ethyl at 3, double bond at 3, and a triple bond at 5. So you would write it out as 3, 3 methyl, 2 methyl, okay, 3 ene, 5 ene. You can do it like this. This is probably the best way to do it. So you can see that you have a double bond at 3 and a triple bond at 5, right? With these suffixes, you have to. Oh, wait, I messed up. There's supposed to be another E here. So 3 ene and 5 ene, right? So this is how you would write the IUPAC name for this one. And step 10 is cyclic. Step 10 is adding the cyclic ones. So those ones are just separate. So adding your cyclic substituents, which are just this is your cyclopropyl, your cyclobutyl. Yeah, that's pretty much it. So these are your cyclic substituents. You can just add them in your main chain as well. All right, let's do a big example with a bunch of stuff in it, right? So if you start here, right, 1, 2, 3, 4, 5, 6, 7, 8. So this is, I add like a methyl here, a methyl here, a methyl here. Let's make this an alcohol. Add a double bond here, right? Then we add a cyclo here, cyclopropyl in this case. So first we have to start numbering the main carbon chain, which would be 1, 2, 3, 4, 5, 6, 7, 8. This is our main chain, right? Now we have to, what's the next step? We have to number the carbon chain, identify the substituents. Let's identify the substituent, right? This is an ethyl. This is a methyl. This is a methyl. This is a double bond. This is a cyclopropyl. And this is your alcohol. Alcohol, right? So once we do that, what's the next step? Name the substituents. We did that already. Group the substituents. Right, so we have two methyls, so it will be a dimethyl combo, right? What's the next step? 7 is to write them all together. 8 is to check functional groups. 8, 9, 10, you just have to do them all together, right? So writing out the name, first we have to do it alphabetically, right? So alphabetically, cyclo comes first. That's one of the ones that we don't skip, remember? So first one would be 7-cyclo. Actually, I don't think that's right. Since cyclo is first, you want to alphabetize it in that direction. So I made a mistake here. So this would be 1, this would be 2, 3, 4, 5, 6, 7. See, I made another mistake if you want to look at it. I counted the main chain wrong. You got 7, you got 8, you got 9. Now you have 3 methyls instead of an S also. Remember, it can be tricky sometimes. Even I can make a mistake. So this is not an ethyl actually. You just have 3 methyls. That is all part of the main chain. So you got 1, 2, 3, 4, 5, 6, 7, 8, 9. That's your main chain. So you have a nonene, well, nonene, nonenal, actually. But now you want to write it out. See, so now we're gonna do the next step, which is group them all together. So we have a trimethyl starting out the name. So we have 2-cyclopropyl. You figure out the name. So 5, 6, 7 trimethyl. And you got non 3 heme 1 all. I have to write 1 all. I'm gonna do it just to make it very clear 1 all. So that would represent this vector. So that was your IUPAC naming. Very complicated, a lot of memorization, a lot of different terms. Let's pause here for a second and catch up. All right, we're back. So just after covering the IUPAC name, so that was a big example of IUPAC stuff. Now moving on, we're going to do carbon classifications, carbon and hydrogen classifications. So if a carbon is bonded to just hydrogens, or if a sorry, my bad. Reset. If a carbon, if a carbon, why is this so small? If a carbon is bonded to just one carbon, like so, then these are primary carbons. If a carbon is bonded to two carbons, then this one is a secondary. Carbon is bonded to if a carbon is bonded to three other carbons, it's a tertiary carbon. This carbon would be a tertiary carbon. And if a carbon is bonded to four other carbons, then it is a quaternary carbon. So what does this mean, right? Um, when you go from primary to secondary to tertiary, your steric hindrance, which I'll cover in a second, steric hindrance increases, stability increases, and bond strength decreases. This bond strength, when I refer to bond strength, I'm referring to CH bond strength, not CC. CH bond strength decreases. Now, for each of these carbons, there's hydrogen classifications as well. So if you have, for example, with primary carbons, these hydrogens would be listed as primary hydrogens. These ones would be secondary hydrogens. And last but not least, this would be your tertiary hydrogen. So a hydrogen attached to a tertiary carbon is a tertiary hydrogen. Similarly, if a hydrogen attached to a primary carbon is a primary hydrogen, and a hydrogen attached to a secondary carbon is a secondary hydrogen. So basically, those are just some classifications that you need to know. So if given a structure something like this, using IUPAC nomenclature, first of all, we should be able to name this, right? And secondly, identify all different primary, secondary. I'm going to do it in a different pen, right? So this would be your primary carbon, primary carbon, primary carbon, primary carbon, and another primary carbon. This is your tertiary. This is your secondary. Right, what would be the name of this compound? So let's use the IUPAC. So we get into 3, 4, 5, right? That's the main chain. You could switch which carbon you want to do. You can do this one or that one, but it wouldn't really make a difference. So here you go. Here's your 5 carbon chains. What is identify the substituents? You have 3 methyls. Each of them are they're at 2 and then they're at 4. There are 3 of them, so you group them together. You have a trimethyl. Any functional groups? None. Any other double bonds? None. Any cyclic bonds? None. So when you're writing this out, this should be 2 comma 2 comma 4 trimethyl pentane. And these are your basic like carbon uh distinctions, right? So primary carbon, secondary, tertiary. And what's important, steric hindrance, stability, bond strength. All right, what is steric hindrance? Steric hindrance is the physical crowding around an atom, usually carbon, that makes it harder for other molecules or atoms to approach and react to it. So if you have a carbon that is bonded to a bunch of other stuff, think about this as a big crowd, right? So this is your quaternary carbon, right? It's bonded to such bulky things and they're blocking all the way. So for a big chlorine wants to attack, right? It's getting blocked by these two carbons. If another chlorine tries to attack from here, it's getting blocked by these two carbons. So basically think about a crowded like flea market or like a concert, right? If you're trying to get to a place, but there's like a bunch of bodies blocking you, it's very difficult. So it's heavily like high energy intensive stuff. Next, what we're gonna move on, we're doing IUPAC is conformations. Conformations. Conformations are motion about a single bond that leads to a series of different dihedral angles. What does that mean? Um, let's take, for example, this carbon structure, right? Cl, OH, and NH. This carbon makes you one, right? So different conformations would be if I rotate around a bond, right? So what I can do is I can keep this bond the same and rotate around it. So it would rotate like something like this. So you would have C, H, NH2, Cl, OH. Another rotate. Then I can hold this one straight and then rotate about this bond, right? So you would have CO, Cl, NH2, H, right? So these are all different conformations of the same like compound. And conformations of a molecule is spatial arrangement of its atom at a when a dihedral angle is specified. So if I specify like the angular shifts and stuff, when I stop it, whatever conformation is the compound at is what I will see it as. So different conformations have different ways of drawing them. So you can draw conformations in three different forms. The first one is your line and wedge, which I will cover as line and wedge. Oh, line and wedge is our first way of writing conformations, right? So how does that work? So what line and wedge do is they give a Lewis structure three dimensions. So some right ways. So let's take a Lewis structure first, right? Before we move on. This is the Lewis structure of, this is neopentane, I'm pretty sure. So this is neopentane, right? And so we know this carbon is sp3 hybridized, right? So it looks something like this. We covered this in the last one, right? This is a tetrahedral shape, right? Tetrahedral in three dimensions. So what a line and a wedge do is it gives it that three-dimensional shape. So if I draw this carbon here, then I draw the different axes. This is the y-axis, your x-axis, and your z-axis, right? What this does, if you have a wedge which is filled, a solid wedge, this means pointing out of the page, and this would be one of your carbons. So CH3 here. The flat lines would symbolize in the same plane as the paper. So flat on the paper. And then a dashed wedge means in the back of the page. So if I were to write it out, the tetrahedral shape, right? You would have so you would have something like this. CH3, CH3, then you got your outside CH3 and the one in your back. That's how you're supposed to draw it. So this one doesn't oh wait, tetrahedral. So I guess this has to be up here instead of down there. My apologies. This is not really correct. This is the correct way of like drawing it out because it's tetrahedral, right? Because it's something like this where you have these two these two guys are in the same plane. This guy's pointing out, this guy's pointing back into the page, and so that's what this would look like. I just inverted it in the XYZ plane, and so that's what this would look like. There are some incorrect ways of drawing the XYZ or your line and wedge diagram. So I'll just show them really quickly. Drawing it out straight with 180 degrees. This is incorrect because the wedges cannot be opposite to each other. Because it doesn't like keep the tetrahedral shape anymore. Because then we would have something like this, and that's not really tetrahedral, is it? It's flat, and then looks like a bench if you think, or like a tent, but you have like a thing on the top. So not really tetrahedral. Um, Another thing would be something like this. This is again wrong because the wedge bonds are not supposed to be on the concave side. This also doesn't look correct because if you like draw it out in 3D, it's just like everything is smushed onto one side, which doesn't happen, and this breaks the dihedral structure. So these two examples are wrong. Some correct some correct examples would be this way. So main takeaway from those is you have to separate all the bonds and the wedge and the dash cannot be opposite of each other. They have to be side to side. So this is one way of showing writing your wedges. This is another way. And this is another way. So you can like pick and choose what fits right with you. As long as you're making sure that the tetrahedral shape doesn't change or isn't altered, you're fine. So these are incorrect and these ones are correct. Next one is a slightly more complicated version, line and wedge. The next one is going to be your Newman projections. Newman projections are slightly hard for people because they don't they aren't able to properly visualize it. So first we'll try to create a simple example and figure out how something would look, right? So if you have ethyl, ethylene, or ethane, something like that, ethylene, ethyl, ethane, whichever one works. If you have ethane, right? And imagine this is again sp3. This is also sp3. So these are both tetrahedral shapes, right? Now imagine in 3D, you're looking from this side, right? If this is your eye, right? And you're looking at it from this side, you would be staring straight into a carbon. The other carbon, carbon C, right? This carbon would be behind, like right here, right? And you would be able to see the hydrogens coming out. So H, 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 right? So there's three different conformations when they're like right on top of each other. Let me do it in different colors actually, so it would be easier to see everything. Uh, let's say you have your three carbons like this, right? So how would that look? You would have your first carbon right here, then your second carbon right behind it. And now you can have them in three different positions, right? Where they're right on top of each other. I'm going to draw them slightly on the side so they are not crazy. They can be right on top of each other. This is called the eclipse. If they're right on top of each other. Then the next way could be when they're staggered. And there's different kinds of staggered we'll cover later. So or they could be staggered like this. You got your other C, H, H, and then H, right? This is your eclipsed and your staggered. So imagine Newman projections are basically you're looking through like one bond. So in 3D, if I were to draw this again in 3 dimensions, 2, 3, right? You would have your first carbon here, bonded obviously to the second carbon here, right? And then in your X direction, your Y direction, and then your Z direction, you got one carbon. Nope, not really Z, it's like on the Z axis, somewhere like over here. This one gets erased, right? And then same thing with this guy, you have your uh, X, Y, and then one pointing out, your X, Y, right? So if they're all together on top of each other, then it's staggered. If they're not all together on top of each other, actually, you can put it on the Z, put it on the side. Once you put it on the Z axis, like so, and it would still have its configuration, right? Yeah, something like this. So this is your tetrahedral, right? Tetrahedral shape, and they're staggered on top of each other. So that's what it would look like in 3D. So those are your staggered and your eclipsed positions. So when you have energies involved with this, you can have different kinds of energies. So let's take an example with butane. Let's use blue. Because butane is one with blue. So if you have butane, right? So you have your C, what another C, which is two H's, and then a CH. 3, and then another CH3. All right, so if you're looking at it from this angle, right, then when you draw it out, you have your CH3 on top, H, H, then you have your H, H, and your CH3. And this is a staggered gouge position. Sorry, staggered anti. It's anti position, not that. Standard anti. This is anti because your two bulky groups, your CH3s, are opposite to each other, right? Now we can remember we can do different conformations. This anti is a conformation for your staggered position, right? So we can do different conformations, right? So if I take the carbon in the back, right, and I rotate, if I take this carbon, right, I hold this bond and I rotate around it, I can move, let's say I move this by just 60 degrees, right? If I move this by just 60 degrees, what happens is those carbons are now stacked on top of each other like they were before. So back with this, you have this guy, right? They're stacked on top of each other because we moved the back one. So these stay the same. CH3, H and H. I moved it by 60 degrees. So you have your other C, your H. H is here, your CH3 is here, and your H is over here. So this is an eclipsed position. If I do another 60 degrees, now it's not position. I'm gonna change it so it says conformation instead of anti position conformation more correct. The anti-conformation, right? Now if I rotate it by 60 degrees again, right, you have your C in the back moving to the side. So you have your CH3, H, and H, right? You got your other C in front, which has your CH3, H, H. This is again a staggered gouge conformation. Right, you can rotate again by 60 degrees. Right, and then you'd have another eclipse, but this one is very high in energy because the CHs are all together and there's a lot of steric hindrance between these two CHs. So you have a lot of energy in this one. This is again eclipse. And then if I rotate it by another 60 degrees, I should be back where I started. Nope, I have to do it twice more before I'll be back where I started. But yes, so you have your staggered gouge, then you have it again right here. CCH3, H, H, now you got your H, got your CH3, got your H. This is another staggered gouge conformation. Alright, moving on another 60 degrees. I'm sure you get the idea, but I guess it's important to just draw these out. Different conformations for these guys. This is another eclipse position, right? This is eclipsed again. And then once another 60 degrees, now I should be back where I started. And it's a little bit, but we go nonetheless. C is 3, H, C, A, H, D, 3. Right, and this is staggered by confirmation. All right. So now what does the energy, I'm going to zoom out and draw the energy levels for all of these different positions. So if you have something like this, right, what happens is you start down here, right? This is the lowest your energy goes. Then you move up to a staggered position, then slightly less energy, right? Then you move. Oh, I should probably do it in terms of when they happen, right? So here, let's do it like this. I know these are slightly close together, but I think the graph would be better if I did it like that. So you can see how that works out. All right, so we start here. Since these are anti, this is the lowest energy form possible. Then you go to eclipsed, which is slightly higher. Then you go to staggered gouge, which is a little bit lower, like higher in energy than your lowest level, but lowest nonetheless. Then you go to your max eclipsed. This is your highest energy. Then you go back to gouge, right? Then you go to your eclipsed again, and you're back. And this is cyclic, so these points are your eclipse points where you're higher at energy, right? And then once you're at your lowest of lows are your anti confirmation. While the other ones are gouge. These guys are gouge. I mentioned this in my earlier video, the first one, where I talked about how holding something with high electron in one spot is high in energy, and something similar happens here as well, where if you were holding uh, two very bulky constituents like a methyl group close to each other, that takes a lot of energy. In this case, it's around 22 kilojoules per mole. This is 22 kilojoules per mole of energy, while at these other spots where you're not holding two bulky substituents together, this is 15 kilojoules per mole of energy. Um, at the lowest, like the anti position right here, down here, it's only 3.7 kilojoules per mole of energy. Yeah, so it's pretty low as you can see, right? And this is like somewhere around like 7 or 8 kilojoules per mole of energy. So as you can see, it's very um, varying, but it makes sense, right? When you're staggered and you're anti of each other, you're the farthest distances away. And so that means you have like the lowest amount of energy needed to hold that spot. So some conformations are more preferable than the other ones based on their energy requirements, which is what this Newman projections teach you. Um, I mean, with Newman projections, you can basically learn the other part, which is your Horsaw projections. Horsaw projections tie back to line and wedge, so I'm just gonna write it out. Your horse Sawhorse, sorry, Sawhorse, not horse, Sawhorse projections. right? They're basically line and wedge, but with butane, right? So if you have butane again, since it's tetrahedral, you're gonna have something coming out, right? Something going back, and two bonds in the same plane. And then you'd have another one with one bond in the same plane, something coming out, and something going back. Mhm. Oops, I draw the wedge wrong. I drew the wedge wrong. See. This diagram, okay, I'm gonna just draw CH3, uh, CH3, H, 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 and H. Right? This diagram is basically if you're looking from like back over here, right? Your eyes are falling here, so this guy's coming out. So this would look something like this when you draw it out. And this is basically what a Horsaw projection is. And so you can convert, yeah, Horsaw projections are basically line and wedge just of like 2D, of like more than just one carbon when you're taking a look at multiple carbons. It's just a sideways view of your Newman projections and just line and wedge in a different like form. So you can use sawhorse projections to interconvert between line and wedge and Newman projections. Yeah, that's pretty much it for horse. So I'm not really going to go deep into it. It's how much you have to know. The next thing we're going to cover are physical properties of hydrocarbons. Properties of hydrocarbons. Boiling point. Uh, if you have an unbranched alkene, just gonna cover whatever's relevant. I'm not gonna add extra detail. It's already too long. Unbranched alkenes. As you increase the number of CH units, I talked about this earlier, you increase your boiling point because you're adding more bonds, more carbon and hydrogen bonds, so it increases the number of electrons and things like that, which increases your dipole-dipole moment, so it increases your boiling point. Same thing with your melting point, unbranched alkenes. You increase your CH3, you increase your melting point. Um, when you have branch chains interfere with your crystal structure. So you have lower boiling points. Oh, sorry, lower melting points and lower boiling points, but it's basically the same thing. And symmetric molecules have abnormally high symmetric more compounds have abnormally high melting points. Yeah, pretty much. Let me find. Here's a fun graph I found. I feel like it would work best by. So you can, oh, that's really small. Let me zoom into this guy so you can see how it looks. So you can see here, change it back to green. So you can see here, right, if you have even number of carbons, when you go from even to odd, in this first case, it drops a little bit, but you can see going from even to even, the growth is much bigger as compared to going from even to odd. I guess here you can see it's like a better example, right? Going from even to odd, it's not really that much, but then going from odd to even is very high, which is because of the symmetric properties of even compound. So yeah, this is basically how that like that's a visualization of why symmetric compounds have abnormally high properties. Another quick rundown for dipole moment. Dipole moment increases as you add dipole moment increases as you add more hydrocarbons in unbranched, obviously. Solubility, not soluble in water. It's important. If you only have hydrocarbons, but if you have like an oxygen or something, like let's say if you have ethanol, ethanol dissolves in water. Um, the general rule, I mean, it's not a rule, it's a guide, like it's a general rule of thumb, but it's not really that general. But if you just want to like quickly check if something dissolves in water or not, for every OH, you need to have at least three CHs, CH3s. If you have something like this, because OH makes like what? I think it's 16 plus 2, right? Which is 18. And this is 4. um, Yeah, sorry, I got distracted. Those numbers don't make any sense. But like, yeah, something like this, right? Where every OH with three CH3s, right? So if you have, let's say, propanol, that dissolves in water, but butanol might not dissolve in water. Simply, if you add another OH to it, then it will dissolve in water, but otherwise it won't. So that's just a quick, like, easy way to figure out if something dissolves in water or not. And for density, yeah, another property. So this is dipole moment, solubility, and then density. Increase CH3 units or hydrocarbon units, you increase density. Those were all in the graph, like in that table I showed earlier, like in the very, very early like pictures. Basically, next is a chemical reaction that we should know with hydrocarbons. It's called combustion. If you take hydrocarbons and you add a bunch of oxygen to it and heat, you can get carbon dioxide and water. I mean, this is a basic rundown of what we use to like break down glucose and things like that in our body. But combustion is a simple like reaction we can do. It's a simple reaction that we cover. Next is R, pH, and ER notation. Another notation stuff you have to cover. Combustion, notation, right? As you saw earlier when I was doing functional groups, I wrote R next to all those different functional groups, and R is just a standalone for any alkyl group. So in a case, or like if you have RCl, something like this, R could be your propane, or sorry, butane in this case, or propane, or your cyclo group, so cyclopentane, something like that. That would be your R group. Your pH stands for your phenyl group. Phenyl groups are benzenes basically. So whenever you see like PH, OH, that would be your phenyl group with an alcohol attached. The position of the alcohol is dependent on where you want it. So it's slightly looser notation. So if you say pH and you put an OH next to it, you could have also written something like, oh, sorry. You could have also put the oxygen like over here or something. It doesn't matter. It's a looser notation. So it's not really like set in stone or anything like that. So yeah, and then AR is for more substituted aromatic, just a more substituted um, phenol group. We have something like this, right? And then you have a CH3. That would be a pH. An example of pH. Okay, pH. Oh, in this case, again, you can have either CH3 like opposite to it, or it can be CH3 to the side, like like so, something like this, depending on how you want to write it. It's a looser configuration, but yeah, pretty much that. So this covers everything we need to know for chapter 2. I hope you enjoyed this video. Just to summarize everything that we did really quickly, we're gonna do it over here. Summarize one. We covered hydrocarbons, what they are, hydrocarbons basically. Right. The next thing we covered was naming stuff. Naming stuff that came under IUPAC and cyclo stuff, unbranched versus branched. Then we did conformations, barely covered isomers. Uh, Isomers were the ones where you have similar chemical formula but a different structure, so constitutional isomers. Right, what else? Conformations we did. We did the different notation and physical properties. I hope it all makes sense and it was very helpful. I will be posting questions. I will be posting like another 1 hour video of combined questions with chapter 1, 2, and 3 together. So once I'm done with chapter 3 notes, there will be a video with 1 hour of just practice problems for all 3 chapters. So look out for that. Um, yeah, that's pretty much it.